So our next talk is going to be on the subgraph isomorphism problem and symmetry breaking by Ruth Hoffmann, please.
Thank you. Thanks, everybody. So I'm indeed going to be talking about symmetry breaking, and I'm expecting to get roasted by Marcus this morning, so that's okay. I handed off my own grade yesterday. But I also want to point out that I'm not a proof logger, so I will be posing questions to you all as to what I think we could possibly try and do for proof logging with this, with the techniques that I'm about to show you. And quite possibly also, if you do have ideas, send them to people who actually understand proof logging, which is not me, but Kieran. Just is on the slide. So, what is SIP? What is subgraph isomorphism problem? Kieran has sorted this yesterday. We're looking for a small graph inside a big graph. What are symmetries of a graph? Thank you, Marcus. We have covered this yesterday. We're just looking at how we can turn around the vertices, whether we're flipping them across a diagonal or are switching them around. We're allowed to do different things to make the graph look the same or look at it in different ways, and we're getting the same thing. Okay, 2 slides down, we're good. Symmetries in subgraph isomorphism problem. Well, we're essentially looking at the symmetries of one graph and the other graph. And then when we're starting to do the subgraph isomorphism problem, we're just going to see what are symmetric solutions. So the moment we're starting to map pattern graph, or are also variables in our case, into our target graph, can we find what the symmetries of our solutions of that pattern graph inside of it? The target graph might have more symmetries than what we're looking for in our solutions, but that is okay. We can handle that up to a point. And so in general, what we're looking for is essentially the symmetries of either a graph on our pattern side or our variable side, or on our target side, so on our value side of things. That's all we're really trying to do, but the different ways that we can or can't do it is the interesting part here. So I'm going to cover 2 out of the 4 things that I've listed on the list here, because Marcus kind of covered those first 2 already, which are static symmetry breaking, what we call fixed symmetry breaking, whether that's arbitrary or informed. At the beginning of search, before we're trying to do and find a solution, we're going to set an order on our variables or our values. I don't care which one you want to do. You could do both if you wanted to. And then we're just going to sort of follow that order throughout the whole thing, and that's how we do the symmetry breaking throughout it. The reason why we're splitting that between those 2, you'll see in a second, is kind of my motivation slide in a second as to why I do think the next 2 are the interesting parts. The next 2 are things that are happening during search, specifically for flexi or flexible. We're constructing an order as we go along through search, and we're going to use that order once we're happy with it, throughout it. And for dynamic, we're actually going to extend and retract an order, so we're going to start creating it as we go along through search. If we start backtracking, we're going to start removing things out of our order and keep adding to it when we go down a different branch. The further down we go, the more overhead we do get in calculation. Here is a quick calculation to find out what we want to be as an order. If it's arbitrary, we just choose whatever we want it to be. Can we just Lex leader on the labels of our vertices if we care? Kieran has a nice heuristic in the subgraph solver where he looks at the degree order. We can do that. Here it gets more complex when we start looking at what order is actually the one that we're wanting to go with and what are symmetries that are coming with it. And how we calculate this, I will talk through in a second. Why do I care about this? Well, very, very initial results on what my PhD student Joe has done. So this is actually all of his work. I'm just trying to be as faithful in the representation of what he has done. And I should say the no-sim lines, the pink ones, the purple ones, I guess, on this, is the subgraph isomorphism solver that Kieran has written with all its bells and whistles on. So we are doing no goods, we're doing restarts, which is why is better than natural or degree order, and actually in a lot of places. I should also say the left graph is the number of nodes that we're searching through over cumulative over different instances. And the right one is our runtime over these different instances. We're only breaking the pattern graph symmetries in this one. Target graph looks very similar. There's a reason why I'm not showing you both at the same time. We still don't have the results, mainly. But when we turn off all the bells and whistles, because currently we cannot deal with no goods or restarts, Naturally, the degree orders start ending up being a little bit worse, but they're still not bad. But our during search have a payoff, a very slight payoff with the overheads, but we do get a little bit faster than those symmetries with everything else. Which in my case things is a good thought as to making Joe do more work and actually finally publish and see that we actually get some results out of it. So we're on track. Now, how do we deal with search and how do we actually build our symmetry breaking constraints?
Is there any fundamental reason why you could not do both what Kieran is doing and the fancy symmetry breaking that you're doing?
When we create the constraints for symmetry breaking, when we create the symmetry breaking or the order constraints, they specifically during search might be interfering with what's there. So we have to think about exactly how the no-goods get created. And the restarts as well. When we have created a partial order or a full order, we might have to restart that as well, which we currently haven't implemented.
I would say the main reason is we think it probably works, but we would never trust that it's actually valid unless we have.
That is the other reason, yes. We've run into many issues. I'll get to that in a minute as well. We've run into many issues when we're implementing the symmetry breaking constraints, and to which oftentimes the answer from Kieran was, how about trying to do some proof logging with that as well? And I was going, nah, we're just going to try and test it. We're pretty sure everything's correct now at this point. I'm pretty sure.
What we find it?
Sorry?
What we find it?
As in, Joe's 2 years into his PhD. If he doesn't get it right in the next year and a half, he's not getting a PhD. That's my quantification of it.
You're willing to pay a pint for everyone in the room, for every buck you find?
I'll have a think about that. It's expensive. Right, so technique. What are we doing nowadays and how are we approaching this? So we're using the stabilizer chain, we're using the Schreier-Sims algorithm, and we're getting actually quite a lot of information out of it. And we're liking that. My postdoc and co-supervisor Joe is a group theoretician, and we both quite enjoy having the additional structure and getting that sort of more information out of it. So we're going to really try and get all the information out of it when we're trying to find the automorphism group for our graph. It doesn't matter whether it's pattern or target graph. So what we're looking for is the automorphism group of our variables or our values in this case. And so we do most efficiently, as far as we're aware in group theory land, is the Schreier-Sims algorithm that finds the whole automorphism group or finds a generating set for the automorphism group. And Marcus has created a really good version of it using C++ and other things in the background specifically because he's looking at it for graphs. So we're using that instead of Naughty, for example. So now, how does it help? And what are the two things that we're wanting to use for our symmetry breaking? Actually, two different things that we're looking for, but we're using both of them in different places. First of all is the orbits, which Marcus has mentioned yesterday as well, is essentially looking at all the equivalence classes as to where things map to, and are sort of nice bubbles of things that are equivalent to each other. And the second thing is, whenever we do an assignment, or what in Schreier-Sims world and group world is called stabilizer vertex, we're looking at what we can still map to, and there is a bunch of permutations that we get out of it called the transversals. And when we use those transversals, we get a little bit more information than just using the orbits, and they're technically also giving us a little bit more information than just using the whole generating set of the automorphism group. So trying to use these additional permutations that give us a little bit more information, we believe, and to be fair, looking at how many nodes we remove, it does give us a little bit more information than our orbits, and each of those can give us a different order over the graph that we're trying to symmetry break over, which is great. Everybody happy with this? Everybody believe me that this is okay? I know I've not gotten any proof logging into this yet. Give me another 3 slides, I think. Okay, so that's how we find out our orders. So when I generate constraints, okay, I'm giving it away. This is how we can flip stuff around. So AB means that we're flipping things around, and ABC means that we're doing the circle that I showed you a few slides ago. That is kind of giving away what our generating set is, and what the Deja vu would give us back as a generating set. But when we start doing the assignments, and I'm ignoring what my pattern graph for the moment is, I'm just going to look at what's going on. Sorry, our target graph is. just going to assume that we're making an assignment on A. But when we fix A, when we stabilize A, what do we get? Well, then everything that we could have reached over A is now orbit in our equivalence class. So we can now start creating and say, okay, A is going to be a representative of that class because that's the one that we've stabilized. And so A is going to be less than B and A is going to be less than C because we know that that's symmetric to A. And then we're going to do a next assignment and we're going to stabilize B. When we stabilize B, then we have to consider, okay, now that we stabilized A, we're now stabilizing B. What is still in the orbit of B? Well, just C, because that can be still, in this specific case, after we've stabilized A, B and C can be still swapped around, but we can't do the circular swapping around anymore because A is stabilized. So what can we do? Well, we've got an orbit that's consisting of B and C, so B is going to be less than C. And the last, sorry, yes.
Like a super stupid question. Stabilize. Does that just mean that I'm still interested in all my symmetries, except you're not allowed to shift vertex A around?
Yes, exactly. We fix it. We're not allowed to do anything to it anymore.
Okay.
And so we now look at the graph and see what symmetries we've got left.
Okay. Thank you.
Thank you. And then the same thing happens when we stabilize B and A, and we look for what we can do with C. Well, now C is by itself, nothing else can happen, so we're not adding any additional constraints. When we do this Turing search, for Flexi, we were going to just introduce as we see A, B, and C, and so on. If we backtrack, we don't care. We'll just wait for another new vertex to come in, and we're going to start adding constraints based on that. In dynamic, we were going to create A, B, and C, and then when we start backtracking, say we backtrack from the decision that we made for C and B for some reason, and we go back into A, the constraint B less than C gets removed. Yes, Florian.
How expensive is it to compute this symmetry between B and C once you fixed A? Because it's not obvious from the isomorphism group, from the set that you can do it, right? You need to apply first this one symmetry and then the other.
Yep. So what Shire Sims gives us is once we've stabilized one of our nodes, we get a pointwise stabilizer, which is a subgroup of our original group, which will tell us all this information. I've not written it out here. Maybe I should have added that. Sorry. Yeah. So we get the subgroup of this original group that is specifically stabilizing A, and so we know what's going on in there.
You're saying like once basically Marcus tells you not only this, but also gives this all useful information what sort of happens once you start stabilizing.
Yes. Okay. Any other questions? I know it's a lot of group theory. Sorry. So what do we have? What we currently have proofs for validity, mathematical proofs, not proof logging proofs. For validity is if we're doing this. I should possibly also say. This specific example looks just at the orbits. The algorithm looks almost the same, except for that we're trying to extract something slightly different, namely the transversal at each step. So we can do both ways. We have done both ways and have proofs of validity to do both ways, both over target and patterns in separate. And why they work or don't work together when we're trying to do it. Specifically doing orbits over both of them doesn't work because we start ending up interfering with the equivalent sets with each other. We acknowledge that some of this will be computationally heavy, so we get more computation that we have to worry about when we start worrying about targets and orbits and pattern transversals. But the way we've set this whole thing up, or the way Joe has approached the whole thing, is that actually using this approach and thinking about it, what order things are getting stabilized over, what the orders that we're doing the assignments over, this should be applicable for static, flexi, and dynamic ordering as we go along. With the static one, just calculate what we want to do the assignments, and we calculate that whole reasoning over that before we start doing search. With flexi and dynamic, we do it during search whenever an assignment comes in. Okay, so that's the decision problem. The reason why I've split this up is because we're also really interested in counting. Because in the counting, we're hoping that actually we are getting better results in terms of runtime and cuts, pruning, because Kieran's Glasgow subgraph solver it's very efficient, annoyingly so when we're trying to get any output out of that. So we try to throw the counting problem at it and see what's going. Right, what have we done? We've done everything separate. We know that it works on orbits. Joe has the implementation for transversal, and I think we are almost considering the mathematical proof to be correct. There is one more thing when we're trying to do some of the counting that is currently going wrong in the proof, and we haven't got an intuition exactly how to prove it. We're trying to get results out of it. So we're going to hopefully see better overheads, better results when we come to the counting problem, when we get to the counting problem.
What does counting even mean? Like you're doing massive symmetry handling and then counting as if no symmetry had been applied, or you want to count symmetric? No. So you're getting the original count.
You want the original count back. So we would want to have 6 solutions for this. No, yes, 6. Almost said 9 there.
Basically, you want to do, just to understand, you would like to do this here. You would do massive symmetry handling in some way. You'd find one solution and you'd have but then the proof would be, I see now that obviously these are 6 solutions.
Yes. With the knowledge of what the group is like, or what constraints we have used, we can reconstruct this really easily. In some cases, it's just as multiplying by the size of the group. And I do say some cases because most of the cases, unfortunately, isn't, and we have to keep track. Which gets me to the problems that we're running into. So what did we struggle with when we're trying to create any of this? We ran into the issue of constantly creating order constraints that were conflicting with order constraints that we weren't aware of existed previously or were overriding us on what we were doing. Kieran has such amazing propagators that they got really annoying. And so we kept conflicting with him as well when we were trying to implement it. All this maths that we've created originally that we were happy with started to conflict with what Kieran had in the solver already. And a bunch of times we ran into issues when we started to undo constraints. Now, Kieran claims that we should have been able to debug all of this using proof logging. I am not completely sure about it, Kieran, if I'm honest.
It would tell you exactly what you were doing. Proof logging doesn't just say no, but proof doesn't work. It says proof line 27, which you outputted using your line of source code 35, is outputting nonsense.
I mean, so, fair. Except when we start undoing and removing constraints, that will be more troublesome, right?
It tells you the first time you do something stupid. It tells you which bits of your code did the stupid thing. That's powerful. I mean,
do we send some tense?
Oh, no. I'm just not going to make Joe do this, unfortunately. We're not proof logging experts. I'm not sending Joe off for a year to ask him to learn proof logging. There's no tension at all. Upcoming issues. So when we do counting, we have encountered this already. We're over counting, simultaneously under counting. We don't know whether we're counting the right solutions. Or whether the solutions that we're looking at are actually solutions, but then the multiplication that we're doing is giving us the right count. There's a bunch of constraint tracking that we have to do when we're doing the counting because of the way we're symmetry breaking, because the symmetry breaking does not necessarily have to be complete. And even if it is complete on our targets, that means nothing for the counting. It gets messy. And I do think actually having proof logging, and here is where I'm agreeing with Kieran, the proof logging would actually be quite helpful on this, because if we are suddenly creating a symmetry breaking constraint that, for example, gives us a solution where there shouldn't be one, or it creates a solution that isn't the solution in the first place, then we should be aware of that, and we should be aware to be able to track it in the first place. Yeah.
Do you think the overcounting or undercounting is due to unsound symmetry breaking, or is there something?
No. So the symmetry breaking is still sound because we've validated it. It's the way we are tracking of how many solutions we've cut out is not necessarily complete. So we've run into issues there where we have got 2 solutions that we haven't identified as being symmetric because we're not doing complete symmetry breaking necessarily, mapping to a same solution that we've identified to be symmetric to those. And so we're over counting because we don't have that connection between those.
Not immediately seeing that very PB proof logging would help too much with this, because there's no counting inherent in very PB.
So we are adding this is a good question to ask Joe. I believe he's adding additional bits on top of the constraints to do the tracking as to exactly how many additional solutions we're counting from a specific constraint. Not sure, you're very right. I'm not sure whether proof locking will be helpful with that still, but keeping track of that would be just useful for us. And when things get fired and when, especially in the undercounting, yes, wrong when something's gone off. Challenges for proof locking, and I will open this up to everybody. Fixed, arbitrary, informed, which is the static one. Thanks to Marcus, I don't think that's a problem anymore. And I do agree, yes, our problems are too small. So I think that is not really a challenge anymore because we're creating the constraints beforehand. We've got them already in the system. We could go over that, that's fine. Flexible could be a little bit challenging, mainly because when we are creating that order during search, we might have to adjust what we're proof logging and how our proof logging is actually done. But I'm not necessarily seeing a big issue with it unless somebody shouts at me right now. On the other hand, dynamic, I am seeing more problems coming through because we're extending and retracting. So we're adding and removing constraints and we're rechanging them around. The same constraint might be added at one point, removed, and then 4 branches down might be reintroduced because that's the way the symmetries come about, or we completely ignore for the rest of it and actually switch around to something completely different. So I suspect that even for the decision problem, this might be problematic when we're trying to do proof logging in the dynamic way, the way I've described it here, not any other dynamic symmetry breaking techniques that you've heard of before. For the counting problem, fixed should be okay, so static symmetry breaking should be okay because you should know how we're retrieving the number of solutions from the get-go. Think it's not necessarily multiplication, but we know how we're tracking things. We know the order from the beginning. Inflexible, we are building a specific count retrieval. We're not undoing it, so we should be okay with that. I think we should be able to settle on a proof with the counts in that. In general, I know counting is not an easy thing for proof logging, or as far as I understand it, at least. And then, dynamic is going to be a pain, I believe. That's my opinion, and I'm quite happy to be overridden on that. But because we're already struggling with knowing which solutions have been pruned, symmetric solutions have been pruned, and which have not. For that matter, if we have pruned, have we accounted for them? Are we getting to reprune them and re-accounting for them? That's the biggest issue that we're currently running into, and I suspect proof logging might do as well, because there is not necessarily related constraints that are giving us the same solutions that will be identified to be the symmetric solution. Right, I'm going to wrap up and say thank you to Joe, who did all the work and let me present this here today. He is working on subgraph solver at Hoffmann, and there is a separate branch that you can go in and start messing around with and deal with on that front. And I'm quite happy to have questions, hard or easy ones, and or suggestions as to what we can do better or not, or how this could look in proof logging. Thank you.
So there's plenty of time for questions.
The questions, Marcus? Yes.
Maybe a small remark. So for the static symmetry breaking, so the technique that you showed, we usually, so in this would be called Schreier cuts.
Yeah.
And usually for static symmetry breaking, we try to guess from the structure a nice ordering, a nice set of generators to produce basically ad hoc without descending a stabilizer chain. And if you just do the stabilizer chain, it's not really surprising that it doesn't perform well.
Yeah.
Because most symmetry breaking are kind of bad. And sort of the whole point usually is to guess from the structure a nice ordering, nice structure. And I think this could also occur in the subgraph isomorphism solver. That you can guess from the structure with nice constraints, which would perform much better.
And then what you use as a static symmetry breaking at the
Yes.
I'm quite happy to accept that, especially since in our initial calculations, if we were to take an actual order, we were performing worse than when we were looking at the degree order, which is the way that Key and subgraph solver usually approaches the symmetry breaking. once we integrate no goods and restarts into it as well, I suspect it will perform by miles better than what we're doing in Flexi and in Dynamic. But I'm just already happy to see that Flexi and Dynamic are not doing as bad as all the theoretical papers in the past have said, and just said, or just use Lex Linear, right?
Yes.
Or the row column symmetries, right? So we're doing already a lot. Impressively, I'm really happy with that. We're doing better on this and sort of going, okay, we've now reached a point that we should be doing this as well.
Yeah, but even in your example, you produced like A less than B, A less than C, and then B less than C, so you could have just skipped A less than C.
Yes. I'm never not going to claim that we're playing to more constraints than we should.
So that doesn't actually make a difference for CP, because CP has a propagator that you throw in all of the order constraints, and what it actually does is it rewrites the order constraints into this like acyclic structure. So it's not like in SAT where if you throw in a bunch of these extra clauses, they take time to propagate. What the CP propagator takes an order and it efficiently propagates the consequences of that order. And the only thing about the A is less than B is less than C, A is less than C, is you give it 3 constraints to work out how to turn into a tree rather than 2 constraints to work out how to turn into a tree. And that bit is super fast anyway because you only do it once.
Yes, but these are also only bonds, right? So you could be producing like deeper constraints. And I think then it does matter which ones you use. At least would be my guess. It may be that in the subgraph problem this only starts to really matter once you have both at the same time, pattern and target. But
maybe for target symmetries it's more complicated. For pattern symmetries, no matter how many of the binary relations you give me, the propagator runs at the same speed and does the same amount of filtering.
It might be an issue when we do both. I suspect Kieran's right that we'll start running into issues when we're just doing targets with just domain symmetries. Symmetries. I think we might be starting earlier than when we start combining them.
Even then, for target symmetries, you can it still builds up the static ordering that you run the constraints in.
Yes, I don't think we've even looked at how that influences anything that we're doing. We're not considering the order of the constraints that they're covering, but we're propagating over.
More questions for Ruth?
You're working on counting and not on enumerating, and that's less a question for you, but for the others. How would it work in VeryPB to argue about counting without arguing about enumerating at the same time? Because enumerating is a harder problem than counting.
I have one crazy idea. Okay, I have actually constructed proofs to do this for very, very small toy problems. So we have check deletion, and we know how to use redundance in such a way. There's a restricted version of redundance that doesn't change the solution count. So, for example, I can reify on a fresh variable, and we know that this won't add or delete solutions. So potentially, I take my input, I do a whole lot of work, and then I output a very specific PV formula, having deleted every remaining constraint. So if I have a proof which preserves solution counts, if all my input variables are X variables, and the entire database at the end of a proof is Y1 plus Y2 plus Y3 equals 1, Z1 plus Z2 plus Z3 plus Z4 equals 1, then I claim that I have given you a proof that there are exactly 12 solutions. This is sort of like compiling to a decision diagram, in a sense. The argument is, I was looking at this for decomposition proofs, like decomposition and counting specifically. The idea is if your proof system preserves counting, and if you can delete the entirety of the input and output some totally fresh stuff in a very convenient format where it's easily countable, then effectively I have given you a proof that counts at the same thing. Okay. And then you need a little toy program that says, given a very, very restricted class of PB formula, I'm going to output the solution count for the formula, and you need to trust that.
But it's worth noting that the only state-of-the-art model counting that I'm aware of, the framework does exactly this. So somehow you could basically go in two directions. Either you can enrich your calculus to be aware of solution counts. There are proposals for this, but I don't think they've been implemented in any generality and been shown to work. The one approach that does exist, where they're actually, I mean, they have code and they publish papers where they actually have evaluated things. Then this is this POG approach, and which does exactly this. You do a rewrite of your input to an output formula, and the proof semantics are that all your rewrites are count preserving. Okay, and then the output formula, you say, oh, this is such a simple formula, just look at it and count. You should be able to do this. And then the proof is, well, if my output formula is x1 plus x2 equals 1, y1 plus y2 plus y3 equals 1, then I claim that Simon, figure out that this is 6. I don't care how you do it, you should be able to do it. And then what I'm proving to you is you had this humongous input formula, and in a solution preserving way, I transformed it step by step into this x1 plus x2 equals 1, y1 plus y2 plus y3 equals 1, or if I said it the other way around.
That's count preserve solution.
Yeah, okay. So, well, it will it will, yes, solution count preserving, yes. I mean, in particular, the only way we know how to, you would sort of trace some kind of bijection of solutions before and after. But yeah, count preserving.
See Andrea's hand, but I kind of feel like we should move on and take.
Well,
I've had enough. We can talk about it
we
later.
can take a quick question while Florian said that.
Okay, yes. How is that different from enumerate? Like, take.
Oh, because I could have exponential solutions, and I'll generate efficiently a count that says you have 1 billion solutions.
Right, but what you're giving, if you read the deletions backwards and you do them in my way, then what you have is essentially an algorithm that generates every solution.
No.
You want to do this
No.
efficient then. You are
No.
exponentially worse when you generate all solutions.
No. If you run it, but you have an algorithm that generates all the solutions.
Okay, but could you also get the counts just from this algorithm?
Yeah, it's the same thing that Kieran explained. So you take the proof that Kieran explained, and now what you do is you look at the proof backwards, right? So for every model that I give to the counting formula, right, that you have at the end, then by reading backwards the very repeating proof, I have an algorithm that transforms it into a symmetry.
So the question, well, actually when you look at enumeration, every user that cares about enumeration would actually be happy if you outputted a list of sort of unique solutions plus a set of the generators or something similar telling you. And the question is whether your algorithm is still efficiently countable when you run it backwards. Yeah.
Okay, so let's